session number 14 started. My name is Don Davies of Magnuson Klemensic Associates in Seattle, Washington, and today is the first of today's triple track session entitled Advances in Structural Engineering Part 1. We have three fantastic speakers here this morning, and to start it off, the opening presentation will be given by William Baker of Skidmore, Owings & Merrill, entitled Supertalls, The Next Generation. Can we please welcome William Baker to the speaker podium?
Thank you very much. As I said at the opening session, it's great to be here in Mumbai in India, where you have this incredible future in developing these incredible urban areas that you have here in India. And certainly tall buildings is going to be part of it. Now I'm going to talk about Supertalls. Okay, now, and one could argue why have them at all, but a lot of it has to do with dreams and optimism and people who build, the really big ones, the skyscrapers, the developers and the communities that have them are saying something about themselves, and these are like dreams that have been rendered into steel and concrete. And I think that's a wonderful thing. It's part of the human nature to want to have these very special ones. So I'm going to talk about a very small part of the world of tall buildings, which is the super tall. Now, where are we now? Well, we've certainly come a long way in the last 100 years. On the slide, you see what was the world's tallest building in 1909, and what it is today, and certainly we've come a tremendous way. And in each of these cases, as the world's tallest building moves around the world, it talks about a community that's trying to make it smart. That we saw Buttressed Tower before the break. Many people in the world didn't know where Kuala Lumpur was until that happened. And that's a lot of what Burj Dubai, or as I'll keep calling it because I keep forgetting, the Burj Khalifa Tower. So here's currently the world's tallest building. What I'm going to do is this talk is going to have two parts. One is I'm going to talk about a little bit about where we are through the Burj Khalifa. At first I wasn't going to talk about the Burj Khalifa at all, but then I realized that a lot of people in the audience aren't that familiar with it, so I'll give you a little brief overline. Then I'm going to talk about what I think is beyond the Burj Khalifa. The Burj Khalifa, it's around 3 million square feet, about 280,000 square meters in the tower, and a low rise of around 2 million square feet, for a total development around 5 million square feet, which is a lot of area, obviously, but the area in the tower is really relatively modest. That 3 million square feet, or 280,000 square meters, is quite a bit less than, say, the towers of the World Trade Center. They were each around 360,000 square meters. The Sears Tower is around 400,000 square meters. So here's a building which is essentially twice as tall that was able to go with a lot less area. And that's one of the reasons the building happened, okay? That I'm going to talk about a little bit later about why buildings don't get built. And one of the reasons buildings don't get built is they have too much area. Here's the usage of the Burj. At the very bottom, what's roughly a green color is an Armani hotel. It goes up to basically level 15, and it is it's Giorgio Armani's first branded hotel. And it's going to open next month, and that occupies the base. The blue, the kind of orange, and the yellow are residential floors. Okay, and there are different levels of quality, different ceiling heights as you go up, and that takes you from level 19 to 108. Now, what's kind of interesting about this building is the fact that it is mainly a residential tower. If you went back to the mid-'80s, you'd say a lot of things. You'd say the world's tallest buildings in North America. It's made of structural steel, and it's an office building, okay? And now it's none of those things. It's not definitely in North America, and the world's tallest buildings that will follow this one are most likely not in North America. They're probably going to have a lot of concrete in them, and they very well might be residential, and that's one of the reasons I think this building happened also is because it was a residential tower. Anyway, but those part of it is for the financial stream. Those three zones, the blue, the orange, and the yellow, were sold in 2 nights. Okay, back in 2004, there was an invitation-only auction, and so basically these people come who are basically, of course, speculators. They're buying whole floors or multiple floors. at a time, and they actually would. There was actually a black market for the invitations to the sales event, and people would go to the front of the line, they'd buy a unit, and they go to the back of the line and sell it. But I was talking to Imar the other day at the opening, and they said that the people who bought these had to put 50% down after 6 months. So there's a lot of money tied up in there, and now that they're going to start closing the units, they'll get the rest of the money. The pink, interestingly enough, is office space. Okay. Now I'm from Chicago, and SOM, and we do a lot of corporate office buildings. Okay, and so we're used to like big floor plates, lots of people, high efficiency, and we were saying these really don't look like office floors to us. We thought they were going to be palaces in the sky. These are floor plates from about 10,000 square feet, say around 1,000 square meters down to 500 square meters. They're relatively small floor plates. But our client, who knows the market very well, said these will be boutique offices for rich individuals, like a sheikh from Saudi Arabia or someone wealthy from India, who wants to have an office in Dubai. And of course, if you're very wealthy, you'll want to have your office in the Burj Dubai, Burj Khalifa. I'm sorry. Okay, I spent the last 7 years calling this tower the Burj Dubai. I've only had 1 month to learn to call it the Burj Khalifa, so I'll keep making that mistake. And so that's how it would change. There's 37 floors up there, and in the middle of that zone, you'll see a little band, and that little band is where the observation deck. The observation deck is not all the way to the top. At the very, very top, of course, you have mechanical systems and the like, and then above there is the spire. Here's the floor plate, okay? It's a paradigm shift. It's residential. Here you have, if you go to the Sears Tower, at the base of the building, it's 22.5 meters from the core to the outside window. It's a huge distance. If you're sitting in that space, you don't really have a view, okay? Because the floor plate is so large. It's because of the nature of that structural system. Here, you have this building where you have a very normal lease span like you'd have in any residential building, but it happens to be a building that happens to be twice as tall. If you go back to tall buildings, in the past, you go back to the World Trade Center, you had a column every meter, and that column was 1/2 meter wide. So you're basically in a cage. If you went fast forward to the Aon building in Chicago, it used to be called the Sears, the Standard Oil building. It was a 1.5 meter column every 3 meters. So still, it was quite dense, quite hard to see out. And you go to here's a building where you have 9 meters clear. It's like any residential building, and so you're sitting there and you have great views. You can see out. So that's another part of this building we have. I'll talk a little bit about this a little bit more later, but look at the very center. That center hexagon, I'll talk about that a bit. That's where all the elevators are for the entire building. There's 19 shafts, okay? But using sophisticated elevator technology, and Jim Fortune, somewhere floating around here, who's our elevator consultant, there was fairly sophisticated management technologies and shuttle elevators and double-deck elevators and the like. We were able to achieve that with just 19 shafts. Okay, now as you go up the tower, what happens is the wings set back. They set back on a module. My firm is called Ctbuh, Owings & Merrill. And the letters are SOM, but that also stands for stay on module, okay? So it's a rigorous 9-meter module, and the setbacks come back in a very, very regular manner. Here we're up to level 76. We're still in the residential floors. Here's 122, which we're getting into basically some of the boutique office spaces. Okay, what made it possible? I'm going to speak briefly about this. It's a technical challenge. Okay, amazing number of people have drawn world's tallest building, and they just generally don't get built. And they're very beautiful drawings and very beautiful ideas. So what made this one possible? My impression is it's the structural system, it's the wind engineering, it's the integration of systems, and it's construction technology. And by the way, after my talk later today, there's going to be a presentation by Ahmed Abdelrazak of Samsung, who's standing over there against the wall. He's going to be speaking about some of the construction technology. So let me go through these a little bit. The building is basically reinforced concrete. At the very top, when the building gets very narrow, it goes to structural steel, but it's basically a reinforced concrete building. And it's a very simple system, very simple idea. It's made of very conventional pieces, just flat plate slabs, walls, and very few columns. And it took a long time to make it simple. There's an American author named Mark Twain who once wrote a letter to his friend, and the letter was rather long, and he said, "I would have written a shorter letter if I had more time." Okay, to make something simple is a tremendous amount of work, and a tremendous amount of work was put into this, trying to make it as simple as possible. And as you look at it, in the very center, you see this hexagonal core where all the elevators are. And that essentially acts like an axle. The last thing you want to have happen in a tall building, you don't want it twisting. There's a whole lot of reasons for that I can explain later, but that's something you don't want to do. So we created this essentially this pipe, this axle that goes up the building that keeps the building from twisting. But that by itself is much too slender to go to such great heights. So what we did is we stiffened it by these having walls going down the corridors, and then cross walls between the demising units, walls between units, all the way out. And because of that, we came up with a name. We call it a buttressed core. So it's basically this core that's buttressed by the three wings. And if you look at the componentry, it's very, very common. You see off the side, there's a little diagram of a tube. That's like the axle. And then you see a little drawing of an I-beam or a wide flange beam. And that's how the wings work. It's like you took an I-beam and you welded it to a tube, and that's the system. And the I-beam essentially stiffens the center tube. And the way we shape it, like I said, it's on this rigorous 9-meter module. It just keeps stepping back and back and back and that's how it shapes. One of my predecessors, who was a partner who's kind of ran the group when I started. He's from India. His name was Hal Angar. Anyway, Hal was in the office one day. He'd retired. I gave him a set of drawings to go over and bleed on it, get his red pen out and work over the drawings. And he came back and said, it shapes itself the same as Sears Tower. It's a completely different structural system, but it shapes itself the way as Sears Tower. On Sears Tower, the way it shapes is you just stop building part of it, okay? You stop building part of it, and originally there's 9 tubes, and then a couple of tubes fall off, and then a couple more, and then 3 fall off, and you're left with 2 tubes that go all the way to the top. And that's how this is. You essentially you stop building part of it because of the architecture. There's a transition from maybe rectilinear elements to round elements, but that's basically how it goes up. And here's the concept. It's a buttressed core. That's what this guy is. He's got wind forces that are coming against his umbrella. He's using his front leg to hold himself up, and his back leg is his buttress. And that's the idea of the Burj Dubai, the Burj Khalifa. Another very important thing in tall buildings is the management of gravity. I stole David's water. I'll give it back to him in a minute. Anyway, I have 2 of these. One is full and one is partially empty, okay? And if I put them down here and I sort of try to knock them over, the one that's empty is easier to knock over than the one that's full, because I'm using the gravity load to help to resist the wind forces. Another thing, if you look at the bottom of your water bottle or your coffee cup or whatever, there's a rim at the edge. It's never flat at the bottom, because if you have a flat cup, it'll wobble on you. And so we need to learn from the guys who make these water containers. They put the support out at the edge, then you use the weight of the water to keep it up. Here's your water, Dave. Okay. Anyway, and so that's what it is. So we keep trying to push the load out. We keep trying to push the gravity load outward to stabilize it. If you were standing up and I was to push on you, you'd spread your feet out to be more stable, and that's really what we're trying to do. At the bottom of the building, this is the reinforcing. If you look at it, it's very, very modest. It's like you might see in a 20-story building. That's because we have no uplift. We're able to, even if you take our wind forces, the factors of safety and the like, If you look at a storm that happens once in 1,700 years, there's no uplift. Okay? It's because of that, we're able to save a great deal on the reinforcing. And if you talk about reinforced concrete, a lot of times the most expensive thing is the rebar. The second most expensive thing is the formwork. The cheapest stuff is concrete. And so we try to minimize that. Another thing you'll see in a minute is, but through the standardization, we were able to reuse the formwork essentially all the way up. Because even though the floors keep changing, most of the portion of the floor doesn't change as it goes up. There's a magic new material out there called concrete. It's not the same stuff that that our earlier generations worked. The stuff you see on the sidewalk, it's also called concrete, but this stuff is magic. Okay, we have very, very high strength concrete, very, very stiff materials. We used to measure concrete workability in a slump. Now we measure the diameter of the puddle. Okay, so you can really put this concrete in very tight pores. It's a technology we picked up in Korea when we were working with Samsung on Tower Palace 3. The spire at the very top, the building set back so many times that we were no longer able to use the standardized formwork that we'd started from the very base. And so at that point, we transitioned into a steel structure. At the very bottom of the building is a 3.7 meter raft or mat with 194 piles, or meter and a half diameter piles going down into the ground. The settlements of the building are around 50 centimeters. 50 millimeters, about that far. Okay, and there was a tremendous amount of very sophisticated calculations done by various geotechnical engineers, and then there was a page-and-a-half hand calc done by Clyde Baker, who's a fairly famous geotechnical engineer in the United States, and he got the same answer, so we knew it was right. And you can see where the piles are. There's a very, very few piles in the very middle of the building. That's because we're pushing the gravity load out. The thing that controls tall buildings is the wind. When the wind goes past an object, it goes by in an unstable manner. There's a lot of people talk in the earlier conversations about vortex shedding. And if you look at the picture on the right, that's a cloud going past the top of the John Hancock. And as it goes past, it's creating a vortex in the cloud. And every time that happens, you get a little pressure differential in the building. And if that matches the harmonics of the building, you'll have something that's kind of like a child on a swing. A building is an oscillator. A swing is an oscillator. And if the child kicks their feet at the natural frequency of the natural harmonics of that swing, it goes very, very high. But if you as an adult tried to hold them up there, that's a lot of work. But the child is able to do it with just their feet. It's not unlike the failure of the Tacoma Narrows Bridge. Everyone saw the pictures of the galloping bridge, the collapse. The wind was blowing sideways and the bridge was jumping up and down. It was going perpendicular to the wind. And so this is the problem. How do we address this vortex shedding? Well, we did a whole lot of wind tunnel testing. And most of the wind tunnel testing was done, it was done at RWDI, and Peter Irwin's somewhere probably in the room. Then we also did a peer review with University of Western Ontario boundary layer wind tunnel. Anyway, so we did a tremendous amount of wind tunnel. But first of all, you have to know what the heck the wind is, okay? And you get your data from the airport, and the data is taken 10 meters off the ground, and you're trying to figure out what the wind speeds are at 800 meters. So what do you do? Well, you turn to Peter and say, what do you do? So what Peter did, he did a whole series of climatic studies and looked at balloon data and the like plus standard modeling tools to see what the velocity profiles were up high, and proved to ourselves that what we were assuming was conservative. So we interviewed for the project almost 7 years ago. On March 1st, I and two of my partners flew to New York to meet some guys from the Middle East who wanted to talk to us about a building. So it was March 1st, 2003. We interviewed. We had like a 2-week competition. They selected us. We immediately went into the wind tunnel with our competition scheme. So you can see we interviewed in March 1st, and we were in the wind tunnel by May. Okay, just to see what the heck we had. And what we discovered is the building had is this 3-wing floor plate, which is pretty common for a residential. Lake Point Tower in Chicago has the same layout. If you go to Las Vegas, you'll see a lot of the hotels have a Y-shaped plan. Anyway, well, we discovered that there were 6 directions because of the setback irregularly. There were 3 noses and then in between the two noses, we call those tails. So it's got 6 directions. And we got the, and as that goes up the building, it reshapes. And what we did, if you look at the one on the left, this is our first wind tunnel test. The results were not good. Okay, and if you look on the right after our third wind tunnel test, with the bar there happens to be I think it's the 1,000-year wind or maybe the 100-year wind. And if you look at the dotted line goes from one chart to the other, you can see how the forces drop. This is proportional to the forces. And we then later did a whole series of aerodynamic tests, which are very, very important because you pick up higher modes. We then tune these buildings using virtual work techniques. We can tune them like a musical instrument. We can play with the mode shapes and the periods. This is where we ended up on the mode shapes around 11 seconds. Ahmed said he's gotten some readings lately, and we're around 10.8 seconds. So our measured and calculated are very close. And this is what happened. Okay, you look at this chart a little bit. The one on the left is what we won the competition. It was 10 meters taller than Taipei 101. Okay, but we didn't want to promise more than we could deliver. Okay, so we went in there. They wanted the world's tallest building. We gave them the world's tallest building, by 10 meters. And we tested it, and the results came back very, very badly. If you look at the bottom of the chart, you'll see a base moment and then an acceleration, and that's what the results we got from the first test. By the time we got to the final scheme, the building had grown 300 meters, 1,000 feet, and the forces had dropped and the accelerations had dropped through this wind engineering approach of actually designing the wind. And all those setbacks on the building, what they do, going back to the child, every time there's the width of the building changes or the shape of the floor changes, the rate of those vortices change. So instead of having a child with 2 feet that are kicking in unison, it's like having a child with 23 feet or 27 feet, kind of scary idea, and each of those feet are kicking at a different rate. So the swing never goes anywhere, and the dynamics never go anywhere. We even, if you look to the right, we tested one that's bigger than that got built. And if you look at the one on the very, very right, you notice that the moments and the accelerations are less than the one we actually built. Okay. Anyway, so but some of the higher modes were worse, so we weren't able to build that. Of course, integration of systems. These things are like Swiss watches. If you waste 1 square meter, you waste it 160 times. Everything had to be located and identified. Here's the core and the life. Construction technology, it was simple elements, basically a vertical factory, and I leave it to attend Ahmed's session later, and hopefully he'll talk a little bit about it. But basically, we were able to use the same formwork in the center of the building for 156 stories. These are the players that are involved, okay? And here is the building, how it looks now. Now they washed the windows, look pretty good. There's a sample of the window wall outside there. As it goes up, we had an opening on January 4th. Here's the crowd. All the big shots sat in one place, and all the people actually worked on the building kind of had to sit off on the side. And they announced the height. Okay, now I knew what the height was, so I wasn't surprised by that. But then they changed the name, and they didn't tell me. Okay. And so I was sitting next to, it was all done in Arabic, and I was sitting next to a guy who spoke Arabic. I said, "What just happened?" And he explained it to me. Something about, anyway, so there was fireworks down the ground. There's these giant fountains around the base, kind of like Bellagio's in Las Vegas fountains going up. There's more fireworks, then fireworks going off the side of the building. And I'm sitting there as structural engineering saying, is this really a good idea? But they had firefighters at each of the locations. Okay, and so there it is, finished, and it's a lot taller than number 2. It's 300 meters, essentially, roughly 300 meters taller than the second highest. Okay, so so where are we going to go from here? Here's a look at the 12 tallest buildings in the world that have either opened or topped out. And they all have different structural systems, or not all of them. There's a lot of core and outrigger systems. There's a few that are different. The Burj is a bit different. And so let's think about those. And then let's think about what's next. Okay, I got this from some website. There's still a bunch of buildings out there that are in the press saying they're going to be the next proposed Supertalls. But there's been so many that have been proposed to the past, and most of them, and virtually all of them, don't get built. Maybe one or two. Why don't they get built? This is a very important question, and this is why I think they don't get built. I think they're too complicated. Okay, they're just too complex. They're too difficult to construct. There's no, when I say too complex, there's no one simple, clear idea. One of the things we try to do when we create a new structural system, we try to give it a name. If you can give it a really short name, maybe you have a really clear idea. Okay, it's too difficult to construct. It takes too long to build, too slow. Time is your enemy. Okay, you got to get in there. You got to build it fast and get on with your life. And too efficient. They're just too wasteful of materials. Too much structure. Too many cubic meters of concrete. Too many pounds of steel. We've been fortunate we've been able to get a few built. Here's what I think is important: speed. Okay, Samsung showed up on site in the spring of 2005, and they topped out a year ago. Okay, that structure went very, very, very quick. Here you see the construction schedule. You look at it, here's another, this is slightly taller than Sears, 36 months. Here, Sears itself, slightly more than 36 months. Jin Mao, once again, about 3 years. And Trump Tower in Chicago, which we just finished, went pretty close. So this is the kind of time frame you need to be in. Hancock went very fast, even though they had a hiatus because of a construction problem at the foundations. Okay, so I think if you're a building that's going to get built, it's got to be rational. You've got to have a rational idea. It has to be appropriate. It has to be fast to build. It needs to be efficient, not wasteful of materials. And that's kind of an ethical thing, in my opinion, also. You just shouldn't be wasting your resources. And if it's not elegant, no one's going to want to pay for it either, okay? So here's what I mean by rational, appropriate, fast, efficient, elegant. One more point I want to talk about is scale, okay? Limitations of scale. You cannot take an existing building and make it bigger. You got to come up with something new, all right? And limitations of scaling, relate to the things you see here. There's issues with too much space. There's issues of too far from the ground. There's issues of a limit of market capacity, okay? Galileo did a famous study of scale. He looked at why is the bone of a dinosaur different in proportions than the bones of a bird? It's because of scale. If I were twice as tall, I'd be twice as thick, twice as wide, and I'd weigh 8 times as much. Not twice as much, 8 times as much. My proportions would be very different. And so as you go into these super tall buildings, you have to recognize that. If the Sears Tower were to scale up to 2,000 feet or 610 meters, I think the area in it, more than doubles. I think it goes up to almost triple. Because it scales by the cube, just like I would. The Burj actually scales by the square, which is kind of an interesting thing. If you made it twice as big, it's only 4 times as much area. Issues of scale. Here I use as an image Frank Lloyd Wright's Mile High Tower. I'm not sure one actually needs a Mile High Tower. So this one here is like essentially about the same height as Burj, so you can get an idea how big, Mile High would be. And there's, and a lot of times you're just pretty darn far from the grade. It's going to take you a while to get up there. There's issues of elevatoring, market capacity. I can't remember. I think the amount of square foot in Frank Lloyd Wright's Mile High Tower was unbelievable. The market could never absorb it. I think it's hard to get to absorb a building that's more than, say, 400,000 square meters. It's just too big for the market to absorb. So what's the next stop? I bet it's a kilometer. Okay, I hope someone does it soon. It'd be sad if the world's tallest building stopped with the Burj. And, I hope someone else has a dream that's bigger than ours and they actually get out there and realize it. With that, thank you.